Welcome to The Communicator, your quick journey into the world of chemical engineering. I'm Samantha Wright-Vargas, AKE Corporate Events Chair. Whether you're a chemie or just curious, join us as we make chemical engineering exciting and accessible. Time to catalyze some great conversations. Hi, my name is Samantha Wright-Vargas, and I'll be your host for The Communicator. I'm excited to have the inspiring Dr. David Allen here with me today. If you could take a moment to introduce yourself.
I'm Dave Allen. I've been a university professor for over 40 years, the last 30 of which have been here at the University of Texas in the McKetta Department of Chemical Engineering.
Amazing. I wanted to start off. Dr. Allen was a lead investigator for the first and second Texas air quality studies, which involved hundreds of researchers worldwide and had a substantial impact on the direction of air quality policies in Texas. I wanted to highlight in a video by the University of Texas Research, you mentioned, quote, we will reach zero methane emissions from the global energy sector by the year 2030. I wanted to ask you, following that, what originally motivated you to study methane emissions, and why is it such an important piece of the climate
All
conversation?
right. So let me go over those as two separate things. First,
Yes.
the Texas air quality studies, which happened back in 2000 and 2006, and then on to the climate. So to describe the Texas air quality studies, I have to take you back to the year 2000. And in the year 2000, Houston had the worst air quality problem by some measures in the United States. If you look at the air pollutant ozone and ask the question in 2000, uh, where were the top 100 measurements of ozone in the United States? 95 of them would have been in Houston. And so, by those measures, Houston's air quality was among the most problematic in the United States. And the state of Texas had just come up with a plan to try and reduce those ozone concentrations. And so, we were left with a really high stakes question, which is uh, how do we get ozone down? The health effects of those high ozone levels were estimated to be billions of dollars a year in Texas. And the costs of controlling them were going to be billions of dollars a year. So there were a number of scientific assumptions that went into developing those plans. And what we wanted to do with the first and then the second Texas air quality studies was make sure the science was right, that we weren't solving the wrong problem. So we assembled a group of hundreds of investigators from all over the world, brought them into Houston, made measurements for a few months in the summer of 2000, and we immediately knew the plan was wrong. It wouldn't work. And so if we followed the original plan, we would have spent billions of dollars a year and we wouldn't have solved the problem.
Mhm.
What we uncovered was a bit of a surprise, but nevertheless, we uncovered what we should really be focusing on in reducing emissions. And the state of Texas responded, took the scientific advice, developed a new air quality plan for the Houston region that was unique. Nowhere else in the world had a plan like this,
Mhm.
but it was based on the best available science. So we found all that in 2000 and made all those changes within the first year or two after making all those measurements. And then we came back a few years later in 2006 and said, did it work? Did the emissions that we said were the problem go down? Did the ozone levels go down? And at the end of the day, Houston now doesn't even have the worst air quality problem in Texas. And the rates of improvement of air quality in Houston, in the greater Houston area, have been more impressive than anywhere else in the United States. And so the plan worked.
Amazing.
So it was a great example of doing scientific research to answer particular policy questions and then having that scientific understanding acted on by the policymakers.
Mm.
So that's the story of the Texas air quality studies.
Amazing.
And so by 2010 or so, we had addressed that problem in Texas and that ozone air quality program, and we began moving on to other types of problems, and we focused in particular on climate.
Mhm.
And so we decided that we would work on climate from the standpoint of methane emissions, methane being probably the greenhouse gas that you haven't heard of. Everyone is aware of carbon dioxide as a greenhouse gas, but methane is also a very potent greenhouse gas.
Mm,
And one of the potential targets for methane emissions and reducing methane emissions is the global energy sector.
mm,
So, global energy sector emits about 100 million tons a year of methane into the atmosphere.
mm,
And that 100 million tons a year, if you were to put it on a basis that is equivalent to carbon dioxide emissions, would be about 8 gigatons, 8 billion tons a year of carbon dioxide emissions. So if you could take the methane emissions from the global energy sector, 100 million tons a year, and get it to zero,
mhm.
what would that be? How big an impact would that be? And so converting it into an equivalent amount of carbon dioxide emissions, getting global methane emissions to zero from the energy sector would be the equivalent in terms of warming of taking all the cars in the world off the road.
Amazing.
And many of us believe that we can get that accomplished by 2030. In my view, and the reason why I've spent since roughly 2010 working on that problem is I believe that it's the biggest impact we can have in the short term to mitigate global warming, to stop or at least slow down the rate of climate change.
Mhm.
And it's entirely doable and doable at a cost that is probably less than almost any other climate mitigation effort that we can have. So, those are the two main themes over the last 25 years or so of the research that I've done.
Amazing. I also wanted to highlight in that same breath, your achievement for reaching the President's Research Impact Award for this research. I think that's a very amazing accomplishment. In that same breath, also, what have been the most surprising findings? How would these insights shape future climate policies? Maybe talk about some challenges, most rewarding parts of it too. Yeah.
All right, so let me answer those in parts again.
Mhm,
I'll start with what were the surprises? So, what did we wind up with that we really didn't expect? And I'll go back, I'll do one each on the Texas air quality studies and
mm,
the Houston ozone problem, and then I'll do one on climate.
mm,
And so, going into the Texas air quality studies, we had the Houston area, which had this terrible, terrible ozone problem. And we came up with all these scientific hypotheses, and the state, in developing its air quality plan, had sort of underlying scientific hypotheses about what was causing the problem. They were all wrong.
mhm,
We went in there and we made measurements, and the measurements led to big surprises. So, what was the big surprise with the Texas air quality studies? Well, in order to make ozone, you need emissions of hydrocarbons that will react in the atmosphere, and you need emissions of nitrogen oxides to go along with it and participate in the reactions. And how much ozone you form is a question of what's the limiting reactant.
mm,
And so one of the things that was not expected is that there are certain classes of hydrocarbons that are much, much more reactive than others. So, for example, the compound ethylene is much more reactive in the atmosphere than ethane is. And the big surprise out of the Texas air quality study were that there were a small group of highly reactive compounds that were being emitted in quantities that we didn't anticipate. So the emission estimates were wrong, which is why it was a big surprise. And we had these really reactive hydrocarbons, ethylene, propylene, butenes, butadiene, that were being emitted largely from the refining and chemical manufacturing sectors in the Houston area, and that was what was driving the really high ozone concentrations. And that wound up being remarkably good news in that if we were going to stay with the existing plan for reducing ozone, you would have had some very expensive controls on the wrong pollutant.
Hmm.
And what the science told us was that these highly reactive alkenes, ethylene, propylene, butenes, butadiene, were the things that we really should be focusing a lot of attention on reducing. And those emissions came largely from leaks and things that were really inexpensive to fix.
Hmm.
And so not only did the plan wind up working better than the original plan would have been, it was also billions of dollars a year cheaper than the original plan. So everybody got benefit. Uh, Control costs were less. We had a better improvement in air quality. It was really uh, a remarkable set of surprises. For the climate work, the surprise that I'll give you is that going into the work, maybe as someone who's worked in air quality for many decades, I should have known this going in. But what we learned was that um, on average, going from the well to the burner tip, if you look at the compound methane coming out of the ground at a natural gas or oil well, getting to the burner tip, about 2% of it leaks away before it gets to the end use. And that was not particularly surprising. What was surprising was that most of those emissions, over half, come from what have come to be called super emitters. So, um, super emitters are things that aren't in there by design, they're malfunctions, they're emitting at really large rates. It's because things break. And we didn't expect that those would be such an important part of the problem. But again, i- if we just fix what's broken, that winds up being a lot less expensive than many other attempts at reducing emissions. Maybe it shouldn't have been a surprise because uh, I should have known that there would have been super emitters. Probably even you should have known that there would have been super emitters, and that we all experience super emitters in our daily lives. People who study air quality like me have known for decades
Yeah.
that 10% of the cars on the road give us 50% of the emissions. And you've undoubtedly driven behind some of those cars, right? And it's because they're old, or it's because they're broken, or it's because somebody has intentionally disconnected the emission control devices. And it winds up being the same thing in the oil and gas sector. And we have these super emitters, maybe we should have known, but that was a big surprise.
Yeah. I assume it's so nuanced you kind of just look over it. Let's go into sustainability. I know that's a big part of what you do. Um, Wanted to ask you, as previous director of the Center for Energy and Environmental Resources at UT Austin, how did you foster the cross-disciplinary collaboration between engineers, chemists, atmospheric scientists, and policy experts to address these challenges?
Yeah, so let me give you and build on a few of the examples of things that I've worked on of how we brought together these multidisciplinary teams. So going back, for example, to the Texas air quality studies, we needed meteorologists, we needed atmospheric chemists, we need people who flew the airplanes that we had our sampling equipment in. We needed all sorts of expertise to do the science in the first place. And so, what the University of Texas is particularly good at is bringing all those people together into big teams. There are no barriers that inhibit you from doing that. But one thing that doesn't happen all that frequently then is taking all that science. Normally, as scientists or engineers doing research, we publish our papers in scientific journals and we try and get that information out. But what we did that was different in all the work that I've done is try to communicate that science in ways that is actionable to policymakers. So I'll tell you another story that was I would say, a benchmark in my career. So this goes back to the Texas air quality studies. Um, we had done all the science. We had written recommendations for the policymakers, and we got to a meeting where the state of Texas, through its Texas Commission on Environmental Quality, was going to decide: do we stick with the old plan, or do we take the science and craft a new plan?
Mm.
And we had written this. I had spent about 15 months writing from the time we first saw the results to the time this vote was taken by Texas Commission on Environmental Quality, writing up, here's the guidance to the policymakers. And,
Mhm.
we had written a short 6-page executive summary of it. And um, and I still remember the opening of the meeting. The Texas Commission on Environmental Quality is run by 3 commissioners.
Mm.
And at the time, all 3 commissioners were engineers, including an alumnus of this department, Ralph Marquez. But the chairman was a person named Bob Houston. And Bob came into the meeting and he was holding our little summary. And I'm going to paraphrase him here because I don't have the exact quote. But he opened the meeting by sort of waving our summary in the air and saying something to the effect of, uh, every day I make $1 million decisions with 25 cents worth of data. And today we're going to make a multi-billion-dollar decision. And I finally feel as though I have enough information to make that decision intelligently.
Mm.
And so that was really what we were trying to do with all the work, to allow policymakers to craft effective, intelligent policies.
Mhm.
And that really came through in that air quality work. But it takes effort, and you need to understand the policies, how the policies work. What we're doing right now is that probably what will drive methane emission reductions from the global energy sector more than anything else, given the current political realities, is the market.
Yes.
And so, what the market is doing right now, and for example, the European Union, which is the largest natural gas purchasing region in the world, they are putting in place what they call border adjustments,
Mm.
called a tax, called a tariff, or called a border adjustment. It places a fee on natural gas coming into the European Union that has greater than a certain amount of emissions.
Mm.
And so they're putting that regulation in place right now. We're working directly with the European Union about, how do you do that? What do you measure?
Mm.
How do you report those measurements? What are the rules of the road of calculating the emissions? So, communicating with those policymakers and making the science usable and actionable for them is something that's uh, what we've done over the last several decades.
It's amazing. Maybe like turning on that, so on the topic of like your work on sustainability, but I know you teach a few classes, such as design for environments and sustaining a planet. Would you like to give us some insight on these classes?
Sure, sure. Let's start with Sustaining a Planet, which is a signature course. And if you're an undergraduate at UT, you've taken at this point a signature course.
Mm.
At the time we started offering that course, we being myself and Jay Banner, who's a professor in geosciences, there were no signature courses.
Mm.
And in fact, the university was just considering, should we teach signature courses? Jay had been teaching a course in geosciences on how does the planet work?
Mm.
How does the water system work? How does the atmosphere work on a global scale? What controls the extent of environmental problems? I was teaching a course that looked the same thing from the standpoint of the engineered world. How do emissions and materials and energy flow in all the systems we've designed? And so we combined those 2 courses and it became the first prototype of a signature course. And so it was the first, effectively, signature course.
Oh, amazing.
And we've been teaching it for the last roughly 20 years as the signature course requirement evolved and developed, and have taught it to now thousands and thousands of students. But point that I'll make is that what we began teaching in roughly 2007, 2006 has evolved over time, and our understanding on many of the issues has evolved over time. And we try and do the same thing in for chemical engineering students with design for environment. How do you incorporate environmental objectives into your designs? So that's what I've been able to teach for the last 20 years or so, is those two courses, which are about both incorporating environmental objectives into our daily decisions as well as into our engineering decisions.
Amazing. On that same note, what advice would you give to students or young researchers who want to pursue sustainability research?
Well, my advice to any undergraduate would be do what you're passionate about.
Yeah.
Do what you really care about, and then no matter what, you'll find satisfaction in doing it. If even uh, if if it's only the joy of doing the work itself and working on problems that you care deeply about.
Mhm. Amazing. Very good advice. Also, speaking of which, you knew Dr. McKetta. Would you tell us a little bit more about him, perhaps how you would like to carry his legacy as the new interim department chair in the McKetta School of Chemical Engineering?
Sure. So I knew John McKetta, and his friends called him Johnny.
Mhm.
Uh, and I also knew his son and grandson. My daughter was a classmate of John McKetta the Third as an elementary and middle school and high school student. So I got to know the McKetta family on both a personal basis as well as a professional basis. So I'll give you two different things, one on the professional side and then one on the personal side.
Mhm.
Things that I learned from Johnny McKetta. So on the professional side, um, I got here to UT in 1995, and so John was already officially retired, although
Mhm.
he didn't really officially retire at that point. He would still come in at 7 o'clock every morning, and the first thing that John would do every morning is call alumni on their birthday.
That's so thoughtful.
And
Wow.
he had this huge number of students whose lives he had influenced, and he would touch base with them each year by calling them on their birthday. I like to say back then, at that point in time, my mother didn't call me on my birthday. So and so the fact that John would have that personal connection
Mhm.
to chemical engineers at the university, I think set a wonderful professional example for all of us that,
Yeah.
once you're a Longhorn, you're always a Longhorn. And now you're a McKetta Longhorn.
Amazing.
And so having that personal commitment to the people that you work with, whether that's students and who become alumni or your peers or colleagues, fostering those relationships was a great professional lesson that I learned from John McKetta.
Mhm.
A personal lesson that I learned from John McKetta. John had the practice of at certain benchmark points in his grandchildren's lives. I don't know if he did this with his kids. I was not there at that time, but with his grandkids, he would ask them the question, where in the world would you want to go? What's your
Mhm.
travel destination that you'd most like to go to? And
Mhm.
then he would take them there. And they do the trip together. So the John McKetta the Third's choice was the Galapagos Islands, right?
I've heard of those. Yeah.
And I know that one because he was a classmate with my daughter. But I took that idea, a great idea, and I used it with my own kids. So when they graduated from college, we said, "Where in the world do you want to go?" And we'll go there as a family.
Mhm.
And we continue that to this day, even though it's not necessarily associated with particular benchmarks. So taking the time to go and do things with your family and people who are important to you is another thing that I learned from John McKetta.
That's amazing. We love to hear about obviously his legacy. Huh. Um, all right, and then taking a little detour from that, but I've heard you're also into wildlife photography to some extent. What drew you to this hobby, and um, in what ways has it also like impacted your life, your
Sure.
career?
Well, maybe I'll start with that last bit. In that, my philosophy has always been you work hard and you play hard.
Hmm.
And I, when I play hard, uh, I like to do things that completely take me away from my work life, so that I come back to my work life refreshed, not having been thinking about it throughout a vacation. So I
Hmm.
like to do things that require complete attention.
Hmm.
And so for decades, I've done things like rock climbing and mountain climbing. That's taken me to a lot of wild, off the grid places.
Hmm.
I can't do the mountaineering expeditions that I once could. So now I go um, and like to do things where I can do photography or other things and still enjoy that wilderness, but do things that will have my complete attention
Hmm.
because that brings me back refreshed to my work life.
And you said you keep these pictures in your office.
Well, so I have two pictures right now in the department chair's office, or three pictures. Um, One is a picture that I took of my son doing some ice climbing with me on.
Hmm.
So I was taking a picture of him on a frozen waterfall in Colorado, which is sort of the
Hmm.
ice climbing mecca of the United States. I have another picture that was a trip my son and I took on to a place that I'd wanted to go for 40 years, which is in Alaska and is on a glacier where we took a plane in, landed on the glacier, and then did various uh, climbing routes in what's called the Great Gorge of the Ruth Glacier.
Hmm.
And so I have a picture of us breaking camp
Hmm.
on the Ruth Glacier. So I have photographs that I've taken in the office that remind me of occasionally getting away and having
Hmm.
things that completely engage me.
Thank you for touching on that. And then again, I know you say you like to go completely off grid when you're on vacation. Arguably, probably the best way to vacation. And yeah, if you could just touch a little bit on work-life balance, how you've handled that as a chemical engineer, especially for our fellow undergrads, grad students, trying to tackle this major.
Yeah, so I believe that you work hard and you play hard,
Hmm.
and if you play hard, then you come back to your work really refreshed. So if you're going to take time, my advice would be if you're going to take time off, really take it off and don't
Yeah.
be half thinking about your professional life. So do something that's going to really refresh you, and often you can do that, and it will take less time to come back refreshed than if you're only half getting away. The other thing is that I would give as advice is make time for the people who mean a lot to you.
Hmm.
And for me, that's meant making sure that, to the extent possible, when I go and get away and don't think about work at all, I'm doing that with people I care an awful lot about.
Amazing. Thank you. Thank you for this insight. Was there anything else you would like to add?
Well, I'll tell you a little bit about what attracted me to the University of Texas. I had been a professor at UCLA for about 12 years before I was recruited here, and um, and what really recruited me here was something that I'll attribute to John McKetta, which is the remarkable degree of collegiality and um, support that the department provides to faculty, to students, to alumni. That degree of connection is so rare
Hmm.
that it's something really to be appreciated and to be nurtured so that it's never lost.
Hmm.
So I think we have something really remarkable here at the McKetta Department of Chemical Engineering. It's perfectly appropriate that the department carries John's name because he was really the patriarch that launched that spirit in the department.
Amazing. Thank you so much. Yeah, but we are so inspired by your efforts and impact in the sustainability sector. So inspired by your story. We would like to thank you for taking the time to speak on our podcast. And yeah, we wish you the best. Thank you so much.
Thank you for having me.
Thank you for listening to The Communicator. If you'd like to learn more about UT's Chemical Engineering Department, then check out our other episodes. We hope to see you on the next one. Same feed, new insights.